Hi everyone, this is Mel. Today we're gonna go through chapter 5, functions and relations. So this is a very basic chapter about set notations, set of numbers, interval notations, and inverse functions. Okay, let's start from the start. If x is an element of A, then we write it in this way. So x kind of like belongs to the set A. If x is not an element, then we do a cross on the on this symbol. So if it's not, then it's like this. Okay, if set A is a subset of B, then we do this. We do this one. It's also kind of like a belonging symbol, but that's this one and this one are different because this one is between element and set, but this one is between set and set. Okay, so A is a subset of B, we write A is a subset of B. Okay, if set A intersect with B, so some elements from set A is also from set B, then we write it as this way. So an intersection, the open is open towards downwards. Okay, and union means all the element from A and all the element from B. So elements from both, we use union on the open facing upwards. And what about A take away B? So the set of element A that are not in B. So element in A and not in B. So we say A and then without B, like that. Okay, sets of numbers. So we can put numbers into sets, depends on their properties. So for natural numbers, which we start from 1, 2, 3, and so on, and 0 is not included in natural numbers in our VCE subject. And for integers, we know that it's from, for example, we have -1, 0, 1, 2, 3, and that's called integers. Rational numbers are represented as Q, which is, for example, 1/2, 1/2. That's rational numbers. And real numbers, which is basically whatever is on the x-axis. Okay, interval notation. So to represent a set more easily, if it's continuous, so if let's say we have all the values on x-axis from -1 to 1, including these 2 points, then we'll say it's square brackets -1, 1, 1. If it's not including, then we use a circle, and that's a round brackets from -1 to -1. So use square brackets if you can take the value on the edge. If you cannot, then use round brackets. Okay, so for infinity, it's very special. We do not use infinity for square brackets. We often use it as round brackets. Okay. Relations. A relation is a set of ordered pairs. So the domain is a set of all the first coordinates of the ordered pairs in the relation. For example, in an, XY coordinate, we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102, 103, 104, 105, 106, 107, 108, 109, 110, 111, 112, 113, 114, 115, 116, 117, a random point x and y. So let's say x1 and y1. So this point, the first coordinate x corresponds to the domain. So any values that x can take forms the domain. So if we can take x belongs to all the real numbers. So all the values on the x-axis and all the values on the y-axis. That means actually all the points in the x, y coordinates. So the value that x can take is the domain. The values that y corresponds to is the range. So the second coordinate, the range corresponds to the second coordinate, which is y. So this is x, this is y in our xy coordinates. Okay, for functions, for a function f and an element x, the domain of f, so x is the domain of f, and there is a unique element y in the range such that xy belongs to f. So for example, let's say a simple function. Let's take y is equal to 2x, and that looks like this. So the domain x is all the real numbers, and y is also all the real numbers. Okay, so the element y is called image of x under f. So the function, we can say the f is fx is equal to 2x. So if we put a pre-image, which is x, we put a pre-image in the function f, then we get 2x, and this 2x is equal to y, which is the image. So the function allows us to put in some pre-image, and then we'll get an image. Or we can say the function, we put in x, and then we get y. Okay, a function f is said to be 1 to 1. If a is not equal to b, implies fa is not equal to fb. So 1 to 1 basically is saying, so for every x corresponds to, so for one x corresponds to one y value. If we take x to be a, then the image, if we put in a, must be different with the fb. For all a and b belongs to the domain of f. In other words, f is a 1 to 1 if every image under f has a unique pre-image. So for every y value under the function f, have a unique x value. It's just saying for one x you must have one y, and one y value must correspond to a unique x value. Okay, the implied domain or maximum domain of a function is the largest subset of R for which the rule is defined. For a function f with domain D, so we represent the domain as D, the new function g may be defined with domain A, which A is a subset of D, and rule given by fx is equal to gx. For all x belongs to A, the function g is called a restriction of f. So why is it called a restriction? It's because we actually restrict the domain. We take a part of the whole domain D and name it as A. So if we restrict the domain, we take a part of the domain and call it A, then all the fx corresponds to the domain A will be called a restriction of f. So if we have a function like this, let's say the domain D is equal to all real numbers, and we only take A to be the positive real number, are positive, then from here and onwards is called gx, and the whole function is called fx. So the gx is called a restriction of function fx. Okay? The inverse function. The inverse function is very important. Let's see. If f is a one-to-one function, so it have a restriction 1-to-1. So f must be a one-to-one function, then each element in y is in the range of f. There is exactly one element x in the domain of f. So it's basically repeating the definition of one-to-one. Thus, if f is one-to-one function, then a new function, f -1, is called the inverse of f. And it's defined in this way. So normally we have fx is equal to a function which is equal to y. Now we have f -1x. Sorry, it should be So if we have fx is equal to y, then our input is x and output is y. However, for the inverse function, so it's called inverse because it's actually inversing the input and output. For the f inverse, if we input y, we'll be actually able to get the output as x. So it's inversed. The x should be an input, but instead in the inverse function, it's acting as an output. And for y, it should be an output in this normal function, but if we have a new inverse function, it's acting as an input. So actually the same meaning from here. So the x and y does not actually represent a specific input or output. It's just it's something you can define as. Or you can define even using value a, b, c or stuff. If you define fa is equal to b, then the inverse function will give you fb, f inverse b to be a. So the same here. If, let's look at this one first. If I define my input as y and output as x, so in the inverse function, I will have x as my input and y as my output. So don't be confused whether they say whether they use this one or this one. It's only the symbol of x and y, so you can define them differently. And it's very good to look at the graph here. So if we have f on this yellow curve, f as function f, if we inverse them, it's actually symmetric with the line y equal to x. And you'll get the blue curve, F inverse. Okay, or in our way, so like this one, you can actually have yx if our fx is equal to y. So now x is still acting as an input. So on the x-axis, the horizontal axis, we have x. Then we have a function. The red curve is fx equal to y. Then by symmetry, the purple curve is F inverse. So it's F inverse y equal to x. Okay, so it's the same. So this one and this one are the same. It only matters how you define the input value and output value. So note that they do not actually write x and y on the horizontal and vertical axis because they think it might be confusing to tell you which is actually the input and output. So conclusion, it does not matter how you choose the input and output. If you define the normal function fx is equal to y first, then the input x should be appearing as the output in your inverse function. Okay, maybe it's easier to give an example. If we have fx equal to 2x, so y is equal to 2x, then our inverse f y should be x. So f inverse 2x should be x. And let's draw a graph. If we have 2x, then by symmetry, we're having x divided by 2. And to note that if you want to inverse a function, it must be 1 to 1. So f has this condition 1 to 1 over here. And the domain. So the domain of the f becomes the range of f inverse, and range of f becomes the domain of f inverse. So actually, from this graph, you can see the red curve, for example, 1, 2, 3. And that's not very clearly from here. Maybe let's draw another one. If I have a curve like this, and I do a symmetry, I get another curve like this. So this one, for example, 1, 2, 3, and this one is 2. So the domain of the purple should be 0 to 2, including 2 and 0. The range should be 1, 2, 3. But however, on the red curve, it's very to see that the domain, this one is the inverse one, should be 1 to 3. And the range is 0 to 2. This is 2. Okay, so the inverse domain becomes the range of the normal function. And the range of the inverse function is the domain of the normal function. So all this swap of domain and range of the normal and inverse function is because we flip them along the diagonal line y equal to x. So you can think of it as if we flip x and y, what will happen to the normal and inverse function. So of course, if we flip at x and y, the domain becomes the range becomes the domain. Okay, that's all for today. We went through the inverse function, the basic interval notation, and the set notation. Yeah. Thanks for listening.